the minimum and the maximum. And in fact, oh wait, the trigonomic function and its squared, you have to do product rule. Oh wait, you have to do quotient rule also because there's a quotient on it too.
Welcome to calculus. It gets a lot harder than that.
Oh, everything can always get harder.
Yeah. Okay. So.
You sounded so excited when you said that. Everything can always get harder.
You're saying everything can get harder.
That's true.
Anytime you think it can't get harder, it can get harder. You can make that harder by not using a calculator and doing it all by hand.
Okay, so did we start this section, or is this kind of where I stopped?
That's where you stop.
That's where you stop, yeah.
Okay, so one of the things that we want to do is connect now the pressure and volume and temperature and particle aspect of the gas laws to the kinetic energy. How does the understanding of kinetic energy explain why these gas laws work? So first of all, we've said that the gas laws don't work unless you have particles that make up matter, right? That's kind of a big point here related to the gas laws, the understanding that the gas laws kind of led to the idea that matter is made up of particles. And if you have to have particles for the gas laws to work, if you make it so that the gases become liquids or solids, you still probably have the particles, right? The particles don't go away. So our understanding of the idea that things are made up of particles called atoms, it comes directly from the gas laws. And I'll continue to say that every so often just so you really burn that into your brain. But now we want to understand how the features of the gas laws relate to the amount of kinetic energy that the particles have. What is it about the kinetic energy that these particles contain that gives rise to all of these features? And I'm not going to ask you to know the physics part of this, the physics calculations that are involved, but there are some things that you're going to have to understand about the math of this that's a little bit challenging. So we should be able to understand that. It's probably not a leap of anybody's understanding here to know that if I have a particle that smacks the wall of a container, it's going to exert a force on that wall, right? I hit the wall of the container, it exerts a force. And what we find out is that the idea of pressure can be quantified by understanding how much force is applied to a certain area of the wall. Okay? Now, obviously, if I have a particle smacking the wall here, and a particle smacking the wall here, and a particle smacking the wall here, and a particle smacking the wall there, and there, I've got several particles smacking the wall, hopefully at the same time, and they're going to exert a force on that. But we can say so much force per area. So square centimeter, square meter, whatever the units we want to use are, we can say that the force per area is what we're talking about. And we've already talked about the idea that the pressure is measured in something called pascals, which is 1 Newton per cubic or square meter, 1 Newton per square meter. And it's just one of our ways of talking about pressure. It's just like pounds per square inch, right? Pounds is also a force. Newtons is a force, so pounds per square inch is also a way of dealing with that. But the official unit of pressure, other than atmospheres, is newtons per square meter. So how many newtons per square meter? And have I told you how many fig newtons, that kind of thing? So 7 fig newtons spread over 1 square meter is the force of 1 Pascal. Okay? Anyway, we can relate force to the momentum of a particle. Okay? So the mass of the particle times the velocity divided by the time that the particle's in contact with the surface is going to give us the force, and this mass times velocity is called the momentum. I don't need you to know that, just understand that we can relate the force of a particle to its momentum. How much force it applies to the wall will be related to how much momentum it has. We can also write the number of particles that we have. We don't just have one particle, right? We have a number of particles. But if we know that 1 mole contains Avogadro's number of particles, 6.022 times 10 to the 23rd, we can multiply that number times the number of moles of stuff that we have, and that will give us the number of particles. And then we can say that the average kinetic energy of a group of particles is 1/2 mu squared. And here we're using u to represent velocity. And the little bar over here means average velocity. You could easily just use a v there as well, but your textbook uses a u. It doesn't matter. So with all of this information, and again, I don't need you to know how I get from all of this information to this. Okay, this is going to be the only circumstance where I don't think it's important for you to see how I get from here to here. We're just going to have to recognize that this is what's going on. We could create an equation using physics to describe the pressure of gas particles from a physics perspective. And the equation that we come up with here, if I know that PV, oops, why is that? If I know that PV equals nRT, and I divide all of that by velocity, okay, you can still see the gas law here, but this is from a physics perspective. I've got volume here, and I've got P here. This is going to be the number of particles, right? In our gas law, we represent that with N, but we use N to represent a number of moles. Here, we're talking about a number of particles. We're not talking about a number of moles. We're talking about a number of particles. And it's going to be 2/3 times the number of particles times the average kinetic energy of a particle. Okay, and we're taking the average kinetic energy here because I'm using this to find the total kinetic energy. Okay, if I multiply the average kinetic energy by the total number of particles, hopefully you would agree that gives me the total kinetic energy. Okay, so I could take this here and say that this is the total kinetic energy. Okay, that's the total kinetic energy. So anyway, we can relate the gas laws, we can relate the pressure of a gas to this formula here, where I say the pressure is equal to 2/3 times the total kinetic energy divided by the volume. Okay, that's how I relate this to kinetic energy. Okay, and so since I've said that the number of particles times the average kinetic energy is the total kinetic energy, we can then say this is the kinetic energy. I can multiply both sides of the equation by volume, and I can divide both sides of the equation by moles, okay? And this just leaves me then with 2/3 times Avogadro's number, or 1 mole times the average kinetic energy. So what we can say is that pressure times volume over the number of moles equals 2/3 times the average kinetic energy. And this is the important thing here. So we can relate the kinetic energy to the pressure and the volume, and the number of moles. Now, we take this a step further, and we say that we remember that the kinetic molecular theory says the average kinetic energy of particles in a gas is proportional to the temperature, right? If I increase the temperature, I'm going to increase the kinetic energy. So I can also say then that the sample, the pressure times the volume over the number of moles is proportional to the temperature. As I increase the temperature, I'm going to increase this. And so another point to all of this is that this is all a physics derivation of this law. I started with a physics definition of pressure, and I added a bunch of stuff in for force and area. Okay, I started with a physics definition of pressure, and I continued to recognize that all of this stuff is just the physics part of things. I've added in the kinetic energy, okay? And so we end up saying that since we get this from physics, well, that's the same thing in chemistry, right? That's our ideal gas law. So physics actually predicts the ideal gas law. Somebody had been smart enough to figure that out before Boyle and Charles and Avogadro went through all of their experiments. They would have been able to predict the ideal gas law. They would have been able to say, this is how we think volume will change related to an increase in temperature. Now, usually science works the other way, right? We do the experiments and we make the observations, and then we explain it. So that physics prediction of what the ideal gas law is kind of an after the fact thing. Obviously, we don't know, we didn't think that first and then say, okay, let's prove it with our experiments. We did our experiments and made the observations and created PV equals nRT, and then we said, oh, this is how physics explains it. Okay? So the other thing that we can do is that we can further equate the kinetic energy to the expression R times T. We know that PV over N equals RT, right? Right? And we also know that PV over N equals 2/3 times the average kinetic energy. So now we can say this is how the kinetic energy relates to the temperature. I can figure out how much my kinetic energy is of all of my particles if I multiply, and all I've done here is multiplied by 3 and divided by 2, if I multiply 3/2 times RT. So this is the important relationship because it shows how all of the observed variables of the gas law are mathematically related to the amount of kinetic energy of the random motions of the particles making up the gas and the corresponding absolute temperature. Okay, so we can see that kinetic energy is directly related to all of our variables. Okay, it has an impact on all of our variables here. So, and right now I forget which formula it is exactly. There will be one formula on your test packet that on the AP test formula sheet that reminds you of this relationship. So you won't have to remember this. You'll because you'll always be forgetting. Is it 2/3 or is it 3/2? But anyway, we can quantify the average speeds of particles, and this is something we actually end up wanting to do for some purposes. We may want to know how fast these particles are moving. So we can quantify the average speeds of particles for a mole of particles if we say the kinetic energy, the average kinetic energy equals 3/2 RT, which is what we set up here, right? Kinetic energy equals 3/2 RT. We can relate that to the physics formula for the kinetic energy. 1/2 mv squared, and every time you see this u, you should think v. 1/2 mv squared is the kinetic energy. Well, if I have Avogadro's number of particles, 1 mole of particles, 6.022 times 10 to the 23rd particles, and this is my average kinetic energy for one of those particles, this would be the kinetic energy for the entire mole of particles, which is also what this is. Okay, so the kinetic energy for the mole of particles is going to be relating 3/2 RT, which is a kinetic energy, to Na times 1/2 mv squared, which is also the kinetic energy of 1 mole of particles. And so I can rearrange this, and I can find the actual velocity. Okay, so I can say 3RT, so I'm going to cancel out the 2's there, right? Those 2's are going to cancel out. And then I'm going to say 3RT equals mv squared times the number of particles, or v squared, or u squared, if you want to put it that way, is the is 3RT divided by the number of particles by the mass of those particles. And what we come to realize then is that Avogadro's number, which is a mole of particles times the mass of all of those, is just the molar mass of that substance. So if I took 6.022 times 10 to the 23rd times 1.01 atomic mass units for hydrogen, or 2.02 for H2, that would just be the molar mass of that. So 3RT divided by the molar mass is what we're talking about here. So I could take the square root of that then, okay, and the square root of that is going to be 3RT over Avogadro's number times the mass of one particle, or it's going to be 3RT over the molar mass of one particle. Okay, and we'll abbreviate this RMS, which means root, which is that, okay? Mean, which means this is the average velocity, because we're going to have a range of velocities, okay? And square, because we're taking the root of the velocity squared. So root mean square velocity is what this is called. Now, one of the problems with this, if this is not enough, we have another little tricky part to this, is that in order to work with the values of the gas constant, the molar mass is given in kilograms per mole rather than in grams per mole. We're used to say that sodium's molar mass is 22.99 grams per mole, but in kilograms per mole, since kilograms is 1,000, I'm going to have to say that the molar mass of sodium in kilograms per mole is 0.02299. And we'll use a big M to indicate that molar mass. Okay, so our final formula here then is that the velocity of the particles in a sample of gas, the velocity of particles in a sample of gas, is going to be equal to the square root of 3RT divided by the molar mass. Okay, and the molar mass that we're talking about here is kilograms per mole rather than grams per mole. Now, we also have another problem here, because in this formula, I don't have either volume or pressure, do I? I don't have volume or pressure in here, so I can't use my standard gas constant, which is liter atmospheres. Liters refers to volume, atmospheres refers to pressure, but I don't have any of those, so my gas constant can't use those values. My gas constant in this case can only talk about moles and temperature and amount of joules of energy. Joules per mole Kelvin. Okay, now I want to show you a little unit comparison thing here then. And so if we think about joules, we think about energy, we think about the fact that our energy formula says 1/2 mv squared. Okay, I measure mass in kilograms, right? I measure velocity in meters per second, and if I square meters per second, I'm going to have units of kilogram meters squared per second squared. Okay, I'm going to have units of kilograms, kilogram meters squared per second squared. That is a joule of energy. And I remember that because I just multiply out the units from my formula here, my kinetic energy formula. If this is kinetic energy, then my units work out like that. That's 1 joule. Okay? If I look at liter atmospheres, okay, if I look at liter atmospheres, I want to see how this is going to be equivalent to that in terms of joules. You wouldn't expect this to be representing an energy term, right? But I could show you how liter atmospheres actually is a measure of energy here. Okay, so if I know that pressure, which is atmospheres here, is force divided by area, and I know that liters, so pressure, yeah, pressure is force per unit area, and then I know that volume is what? Or liters is volume, right? Okay, so if I put volume in terms of cubic meters, and I put force in terms of kilogram meters per second squared, and I put area in terms of meters squared. Okay, so force, we might need to explain why is that kilogram meters per second squared. Force equals mass times acceleration. Mass is kilograms. Acceleration is meters per second squared. So force is kilogram meters per second squared. Okay, so I'm going to end up with m squared times m on top, that's m to the 4th, divided by m squared on the bottom. So I'm going to end up with kilogram meters squared per second squared. So liter atmospheres is in fact an energy unit. Okay? Liter atmospheres is in fact an energy unit. But we just don't call it that. But in order for us to understand this, we need to recognize that. So liter atmospheres, though, are out in this case. I can't use this because I don't have pressure or volume in this formula. So now I'm going to have to just say how many joules per mole Kelvin, right? And if I say that liter atmospheres, remember that my gas constant is liter atmospheres per mole Kelvin, right? That's R. Okay? In this case, R is just joules per mole Kelvin. If I remember that liter atmospheres is the same thing as joules, okay, I'm going to get this different constant here, but it's going to have a different number because I'm actually using joules now instead of liter atmospheres. So in joules, this is 8.314 joules per mole Kelvin. Okay, so I want to know what the velocity, the average velocity, the root mean square, mean again means average, right? I want to know what the root mean square velocity for the atoms in a sample of helium gas is at 25 degrees Celsius. So all I have to do here is say U equals, and I'm going to use V, your book likes to use, but I'm going to use V. V equals the square root of 3RT over the molar mass. Okay, and again, remember the molar mass in this case is in kilograms per mole, not grams per mole. So this is going to be the square root of 3 times 8.314 joules per mole Kelvin times 298 Kelvin. Okay? And then helium has a molar mass of 4.003 grams per mole. So this is going to be 0.004003 kilograms per mole. So we're going to say 0.004003 kilograms per mole. Okay? And we're going to knock out the moles here and the kelvins, and we'll have joules per kilogram, or joules per kilogram. We're going to take the square root of this. So if I could get one of you to actually do that, I don't have my calculator out here. I thought I did somewhere actually. My calculator.
I'm getting, how much did you get 1,362?
Yes, 0.639501.
There's hope that I'm doing it right.
I just want to make sure we end up with the right value here. What'd you guys get?
1,362.
Yep. Okay, and that's going to be meters per second. Okay. So equals 1,362 meters per second. Okay. So the average velocity, based on the fact that these particles have a certain mass and a certain kinetic energy related to whatever that temperature is, 1,362 meters per second. So that's a pretty fair velocity, isn't it? If you've got particles smacking against things at 1,000 meters per second, even if they're tiny particles, they're going to exert some pretty significant pressure. And so if you think about all our atmospheric particles smacking against us or smacking against other things, you understand why we're getting such a significant pressure, 14 pounds per square inch for atmospheric pressure. Okay, so I'm going to have to show you eventually here why it makes sense that we need to find that number, but we're going to need to find that number in some circumstances. Although it's not common for those to actually be on the AP test. It's not uncommon for particle speeds and energies to be expressed in terms of single particles rather than moles. Okay, so this is the average per mole, okay, per mole of particle. So the every particle in there has an average speed of that. But sometimes I want to know about the velocity and energy of a single particle. So to accomplish the same thing for a single particle, we need to convert the gas constant to one that will reflect a single particle. So if I say that this is this many joules per mole per degree Kelvin, and all this is really saying is that every degree I increase, if I have a mole of particles, if I increase 1 degree, I increase the kinetic energy by 8.314 joules. That's what that's saying. If I have a mole of particles and I go from 273 to 274, I've increased the amount of kinetic energy by this many joules. And it should make sense that I'm going to increase the kinetic energy of those particles by the same amount for every degree of temperature that I go up or go down. But if I just want 1, I'm going to divide by Avogadro's number. And now this looks ridiculously small, doesn't it? I'm going to increase for every degree I go up, I'm going to increase the number of joules of energy of a single particle by 1.381 times 10 to the negative 23rd joules. But if I remember, I have 6.022 times 10 to the 23rd particles in a mole of particles, then that sort of kind of puts all of that into perspective then. And this gas constant for a single particle is called the Boltzmann constant, or K. Okay, so the Boltzmann constant is the amount of energy a particle increases by for every degree Kelvin that it increases in temperature. Okay, so I've got the amount of energy increase per degree Kelvin for a single particle. Now I need to convert the molar mass in kilograms to mole to kilograms per particle. Okay, I'm going to have to convert the molar mass to kilograms per particle. So since I know the number of atomic mass units, like in helium I have 4.003 atomic mass units, okay, or 0.004003 kilograms per mole. Okay, I am going to have to divide that by 1.66 times 10 to the negative 27 to get the mass of one particle. Or I'm sorry, I'm not going to have to divide that. I'm going to have to multiply this times the atomic mass to get the number of kilograms per particle. So if one atomic mass unit is 1.66 times 10 to the negative 27 kilograms, and I've got 4.003 kilograms or atomic mass units, then I'm going to have to multiply that times that to get the mass per that one particle. So we can calculate the RMS velocity, root mean square velocity of the single particle by either using the Boltzmann constant and particle mass into the formula, or by dividing the regular gas constant by Na in the formula. In either case, we have to use the mass of one particle in the denominator. Okay, so remember this K here, this Boltzmann constant, is just simply dividing the gas constant by Avogadro's number to get the gas constant for one particle. In either case, I have to use the mass of one particle. Okay, so I want to find out what the RMS speed of a single particle of oxygen or nitrogen is at 20 degrees Celsius. So I can say that that's going to be the square root of 3 times, and we'll use the Boltzmann constant, and you would be given these constants of 1.381 times 10 to the negative 23rd joules per degree Kelvin times 293K. And then I'm going to divide that by, so for oxygen O2, the number of atomic mass units in O2 is 32, right? 2 times 16. So 32.00 atomic mass units times 1.66 times 10 to the 27th, negative 27th kilograms. A lot of calculator work for these. 3 times.
Marshall, there's supposed to be a parentheses after, before the joules. Or
Here?
Yeah.
No,
No.
that's a slash.
Oh, that's a slash.
Yeah, joules per degree Kelvin. Sorry about that. Not a parenthesis.
All right. Just clarifying.
Sure.
Thank you.
I get 478.0 meters per second. Okay, so what do you notice about the velocity of a particle of oxygen at that point versus the velocity of a particle of helium?
It moves faster.
Okay,
A lot faster.
so, and the temperatures are pretty close, it's 20 versus 25. Does it make sense that the more massive something is, the slower it's going to go at the same temperature? Right? The more massive something is, the slower it's going to go. This is going to be important for us, and this proves that. I mean, if we'd have multiplied it by 298 instead of 293, the 25 degrees that was in the other one, it wouldn't have increased that value that much. But we see that the velocity of the helium is going to be about 3 times as much as the velocity of the oxygen here. And that's significant because we said that the way that we resolve our confusion about how it doesn't make any difference what the particles are, it just matters how many particles there are as far as the gas laws goes. We resolve that confusion by saying the kinetic energy is 1/2 mv squared. If I decrease the mass, I correspondingly increase the velocity by the amount that will make the kinetic energy the same. Okay, so if these are both at 25 degrees, that and the one above, the helium, was at 25 degrees, and we actually calculated the energy instead of the velocity, we would find out that the energy for both of those was the same amount of kinetic energy. Okay, and that's significant here. Now, because of the large amount of particles in a sample of gas undergoing random motion and collisions, kinetic energy is constantly transferred among particles. So it should make sense that as I've got all of this energy being transferred between these gazillions of particles in a mole of gas, that I'm going to have a huge range of velocities. Not all of them are going to be going at that average speed. There's going to be a huge range of velocities. Some of them are going to be barely moving at all, and others of them are going to be moving a lot faster than the average speed. Okay? So what we do when we talk about a group of particles, and again, this is going to be significant for us later on, when we talk about a group of particles and their velocities, we represent it as a distribution, okay? And the most probable speed is going to be the largest number of particles, right? I've got number of particles with a certain speed here. And what happens is that as I increase the temperature, this curve is going to flatten out. I'm going to have a much broader range of possible speeds. As I increase this temperature from 273 to 1273 to 2273, I'm going to flatten this out because I'm going to have more speeds that these things could be going. I'm going to flatten this curve out, and the most probable speed.
But they will be having the girl and boys basketball tryouts this Tuesday, November 4th in the gym, or November 24th in the gym. It will be after school. The boys, the freshmen and sophomore, are at from 6 to 7:30 and varsity from 7 to 9. And the girls, please check with your coach to find out your tryout times. So it will be this Tuesday, November 24th, starting at 6. Thank you.
Okay, so the day after the governor's mandate for after-school activities to be expired. Okay. So anyway, understand these particles are going to have a range of velocities. And the most probable velocity is going to be the velocity at which the most particles are at that particular speed. Okay? So at this point, all we're saying is that this number of particles has the speed that's represented by this. This number of particles has that speed. This number of particles has that speed. But the most probable speed is going to be the speed at which I have the most number of particles. And that's going to shift as I increase the temperature. Now, the reason that this is going to be important is because we're going to find out that in order for chemical reactions to occur, first of all, in order for chemical reactions to occur, what do I know has to happen to the reactant particles? They have to do what? They have to smack each other, right? If I'm going to react, I have to smack you, right? If we're particles and we're going to react, we have to hit each other. Would it not make sense that the speed with which we hit each other is going to determine whether or not we actually react? If I hit you with this wimpy speed, I'm not going to react, right? If I hit you with a little bit more speed, we might react, we might not. But if I hit you with a really high speed, you're going to probably react. It's also going to depend on the orientation of the particles to each other. So a lot of things have to happen in order for a chemical reaction to actually occur. There has to be a collision. It has to be at a high enough velocity so that enough kinetic energy goes into those particles reacting, and it has to have the right orientation. But if I don't have most of my particles in the speed above which I'm going to react, then we're not going to get the reaction to occur. Okay, so we're going to look at how reactions occur later on, and this speed is going to be important for us. So that's why we're talking about it now. Okay, so let's stop there.